Welcome to the deep dive. Today we're heading out into space, metaphorically speaking.
We are indeed. We're looking at how planets might have these sort of universal blueprints.
And we're doing this by looking at water ice patterns
Yeah.
in other star systems.
Exactly. The focus is on a really fascinating study using the James Webb Space Telescope. It observed this dusty debris disk around a young star, kind of like our sun.
Yeah.
It's called HD 181327.
Okay, HD 1E1327. And it's about 155 light years off.
That's the one. Quite close, cosmically speaking.
So let's get into our deep dive here. What are we trying to figure out from this distant ice?
Well, the big goal is understanding how planets form and evolve, not just out there, but maybe here too, in our own solar system.
Right, and especially how water gets distributed, yeah, since it's so key for life.
Precisely. It connects right back to, how Earth got its water in the first place.
So before we jump to HD 181327, maybe remind us why water ice is such a big deal right here in our neighborhood.
Good point. In our solar system, water ice is, well, it's everywhere in the outer parts. It shapes icy moons, think Europa or Enceladus. It makes up layers inside Uranus and Neptune. And of course, comets, Kuiper Belt objects like Pluto.
Yeah.
They're loaded with it.
And it's not just static frozen stuff, is it?
No, not at all. It drives geology out there. Things like sublimation ice turning straight to gas or cryovolcanism, ice volcanoes, basically. Tidal heating keeps things active.
Wow. And you mentioned it holds clues, like a time capsule.
Yeah, potentially. It can preserve chemical information from the very early days of the solar system, like a frozen record.
Okay, so back to JWST. What did it find around HD 183327 that was so groundbreaking?
So a team led by Chen Shi used one of Webb's instruments, NRSpec, and they definitively identified crystalline water ice in that debris disk.
Crystalline. Why is that specific form important? Didn't we want to know ice was there?
Well, Spitzer saw hints back in 2008, but it couldn't tell the type of ice clearly. JWST's resolution is way better.
Okay.
Think of like messy snowflakes all jumbled together. That's amorphous ice.
Yeah.
Crystalline ice is more like a perfect ordered ice crystal.
Ah, okay. More structured.
Exactly.
Yeah.
And that structure tells you something about the conditions where it formed or how it's been processed. It suggests it's not just primordial fluff.
Got it. And where in this system, this HD 81327 disk, did they find this crystalline ice?
Okay, so picture the star. Then there's this clear gap with not much dust, and then you get the main debris ring.
Right.
The ice they detected seems to be in that ring, and it likely comes from icy planetesimals, sort of like mini planets or planetary building blocks smashing into each other out there.
Collisions creating fresh ice
It
surfaces.
seems likely. But here's the really interesting part. The amount of ice changes depending on where you look in the disk.
Oh, how so?
It increases as you go further out. In the middle of the disk, it's maybe about 8% ice abundance. But way out in the colder, outermost parts, it jumps to over 20%.
Wow, that's quite a difference. More than double. What about closer in, near that dust-free gap?
Almost no ice detected there in those inner zones.
Why not?
Well, the thinking is either the star's ultraviolet radiation just vaporizes it, cooks it away, or maybe the ice got locked up early inside larger bodies, planetesimals, or even planets that we can't directly see.
Okay, so this pattern, less ice close in, much more further out. How does this connect to, theories about how planets actually form? Does this support the idea of a snow line moving over time?
That's exactly the kind of question researchers like Christine Chen are asking. Knowing the phase crystalline and the distribution is super important for the models of how giant planets get built.
Right. Like, did Jupiter and Saturn grab their icy material in a similar zone in our early solar system, where our Kuiper Belt is now?
Possibly. Could HD H11327 be showing us a kind of standard process, a template for how gas giants gather their icy cores?
And that process could then influence how water gets delivered inwards, maybe, to rocky planets like Earth.
That's the tantalizing connection, if this pattern holds up.
So the next step is to look at more systems, I guess. See if this trend is common.
Exactly. Map the ice in other debris disks. Is this increasing ice concentration with distance a universal thing, or just a quirk of this one system?
Because if it is common, that could tell us a lot about how water might get delivered to habitable zones elsewhere, potentially seeding other rocky worlds.
Right. It links back to these really fundamental questions. Was our solar system's formation typical? And the big one, how did Earth get its oceans?
So this isn't just about some distant icy ring. It's potentially about our own origins.
Absolutely. And hopefully future JWST observations will keep adding pieces to this puzzle.
Okay, so to wrap up, the key takeaway seems to be Observing this increasing amount of crystalline water ice further out in the HD 181327 system gives us this really intriguing glimpse. It might be a common pattern in how planets form and how water gets spread around, echoing what we see in the icy outer parts of our own solar system.
That sums it up well. It's a fascinating snapshot.
And it leaves us for the final thought, maybe for you listening. If the way water ice is laid out in a young system is so crucial, could this distribution be a fundamental factor, maybe the factor, in whether life could eventually arise on new worlds? And what does that mean for our search for other Earths?
Something to definitely ponder.